Again, welcome to the afternoon session for the lab. Both of them are afternoon, actually. The one starts at noon, this one starts at 2 o'clock. So right now we're doing the lab. So hopefully you have had a chance to look at the lab instructions. So let me move this out of the way in here a little bit because I want to get to the instructions in the lab, the PDF file. This has a little bit of some work in terms of what you have to do, okay? Including finding the magnetic field on campus. Because if we did this lab on campus, we would be actually having to make corrections based on the magnetic field of where we are, okay, and the date and all of that thing, because it's critical. So let me share with you, first of all, the screen. What is the thing there? What is the share? Share. Lab instructions, which is a PDF file. Okay, so this is the lab. Again, you are asked to actually go through the background information and what we're doing in here. This is trying to find E over M for the electron, the ratio of the charge, the electronic charge, over the mass of the electron. There was an experiment by Millikan, and he was very meticulous actually about it, where he found the charge of the electron. So think of this one as actually the measurements of the mass of the electron if I know the charge of the electron. So that was the first elementary particle that was identified before even the proton and the neutron. It was the electron. In Millikan's experiment, basically, he had the suspended solutions and he used the electric field to suspend the charges there. And he kept on finding basically the different values of the charge. He collected so much data. And at the end, he found that there is a common thread between all of these charges and they come in multiples of E. So that was Millikan's experiment, but we're not doing Millikan experiment. What we're doing right now is the ratio of E over M, and M in here is specifically for that of the electron, the mass of the electron. A lot of this information is basically, at this point, we know that charge of the electron, 1.602 10 to the negative 19. We know actually its mass now, it's 9.1 times 10 to the negative 31 kilograms. So we have a lot of information about the mass of the, and if you ever take physics 4B, this is a common constant that's, what? This is not correct. I think there is a 0 in here. Let me check this number. There is a problem with this constant. It's not correct. Let me make sure I give you the correct value there in case we ever need it. I don't think that we're going to need it, but let me get you the correct. H is 6.62, 6.626 times 10 to the negative 14. So when H bar, all you have to do is just divide that number by 2 pi. So it's 1.054. That's what I was trying to put the cursor in there to move it a little. So it's actually 1.0. Please make that correction if you ever need this value in here for this lab. So the correct value for H bar is not, oh man, this thing cannot go in here. Can I add a comment maybe, or a text correction? What is it? Text editing, text tool. Edit. So this number is 04, by the way. 054, okay? There is a 0 missing in here. So please correct it from your end, okay? If you're ever going to need it, you will need this to be the correct value, okay? So this is a typo, actually. Joule second, that's if it, spin is also quantized integer, half integer of it is H bar. So, okay. So these are some of the properties of the electron. We've seen this law in here. It has shifted. Everything has shifted in this law in here. So basically, this is F equals to Q times E plus V cross B. This is Lorentz force is equal to MA. Okay. So the point being in here is the ratio. We know now what it is. So this is the number that ultimately you're supposed to find. E over ME, the charge is this much, the mass is this much, and the number should be 1.579 10 to the power 11, because the charge is, I mean, the mass is so tiny, and you're dividing by tinier number, so that's why this ratio is actually a big number. So that is the ultimate goal. This is what we want to see, okay, this lab. Again, do not write the objective until you actually go through everything in the lab, and then you can come back to it. Please do not forget it, okay? Or otherwise you're going to lose points in here unnecessarily. This is the setup in the actual lab in here. We have two different voltages, one to create the current, basically to release the currents, and another one to run them through a magnetic field region. I mean, to create the magnet in here that cause them to move in it, and then they will start to spiral, but you would want them to be confined. So you'd want to see how wide their band is, or how wide they will be bunched together coming in there, and those measurements will determine at the end with the voltages, they will determine that ratio of E over M basically. So that is in a nutshell what it is. So the theory, it goes like this. So inside a magnetic field, the only thing a charge can do in general, doesn't have to be an electron, any charge, this is going to spiral down. And we saw that because the acceleration is perpendicular to the velocity, and that is a circular motion. And from here, you're going to get EVB, where B is the magnetic field that the charge is in, is proportional to the square of the velocity. Cancel the velocity from here with this velocity, and you will end up with a ratio of B over R, which is omega, basically, which is the angular frequency. And that is actually the cyclotron frequency. I know we introduced that one when we did the first topic, when we introduced it. And that is basically the ratio of E over M can be written in terms of omega over B naught, okay? So that is one way of finding it. So the electron gun is this one, the one I was describing it in here. So you have a power supply in here that heat up an element. So the element in here, when it's heated just enough, it's going to release electrons. So electrons, there will be basically floating around in here. So what you do in this case, you apply another voltage to accelerate them, to give them velocity. So at that point, they will be coming in a beam. That's what I was trying to say earlier, okay? Beam of electrons that you're going to be zooming in, okay? Now, you use a conservation of energy in here to find how fast they're going to be moving, because as they emerge, barely emerge, you would want them to just come in. The accelerating voltage in this case is going to be delta V, this delta V, times the charge for each and every one of them is equal to 1/2 times the mass velocity squared, because they started from rest. So this heating element, what it does is just get them out, basically, barely out. And then once they're out, they need to be accelerated. And how fast how much kinetic energy they gain is use the conservation of energy. In this case, the final kinetic energy minus the initial kinetic energy is equal to the potential, in this case, the difference in potential. Difference in potential is charge times the electrical potential. So from here, you're going to find how fast they come out. This is just a practical number. They gave you delta V, okay? And what would be the speed of the particle that is both 10 times more massive and 10 times the charge? So obviously the ratio does not change, okay? So you're going to find the velocity in here for the electron, and you're going to find it for another particle that is 10 times massive and 10 times more charge in it. Okay, so when is the speed becomes too fast? So if this V becomes of the order of 10% or more of the speed of light, then in this case you have to drop the you have to drop all of this mechanics, and you have to invoke relativity. You have to get into physics 4D. Okay. So in order not to get into physics 4D and make your problem accessible, you would want to know actually what kind of voltage you can work with, so that what you do in this case is justified by this classical physics. So what you do in this case, put the velocity V to be 0.10% of the speed of light. The speed of light is 300 million meters per second. And you know what E is, you know what M is, you know what 2 is. So the only thing is you're supposed to find the voltage that is needed. So you don't want to exceed that voltage. If you exceed it, what happened in this case, all of this physics breaks down and you have to invoke another physics. Does this make sense so far? Okay, very good. All you make sure in here is that this V is at most 10% the speed of light. In other words, at most 30 million meters per second. Because if it goes 31 million meter per second or 60 million per second or even 200 million meter per second, which is now you're very much relativistic, then this physics is not good. You have to abandon it. You have to get into Einstein's theory of relativity to get into the proper equations. So when we take this V from here and sub it into this expression, where is it? That we have E over M all the way up there. We have E over M and we have V in here. So I'm going to sub that value for V here in equation 1. But V itself has an E over M too in it. So V has an E over M. When I sub it into equation 1, which is just E over M, has a V over RB, not. So then the equation becomes a little bit more complicated, but I have to solve for E over M. If I solve for E over M, it should find this expression in here. Okay? We will use this formula for equation 4 for the next subsection to calculate the charge to mass ratio. So we're going to use this expression now. Okay? If I can find R, the radius of that beam that comes out. Okay? If I know what the magnetic field is, and if I know what by delta V, the accelerating voltage is, then I'm in business. Then I know exactly what I'm doing in here. That I can just use this formula and I'm in business. Does this make sense?
I'm sorry, can you explain what we're doing in problem 3, I believe? Yeah.
Question.
Oh, no, 2, sorry.
Yeah. Question 2 in here, what you're supposed to do is go back into this equation and make sure that V is less than or equal to at most 10% the speed of light, which is 30 million. The speed of light is 300 million meters per second, correct, Sarah?
Yeah.
So you would want this V not to exceed that number. V should be...
Okay, so it has to be underneath 10%.
I mean, put it 10% if you like. Then the voltage, because it's proportional to the square of the voltage, whatever you come out from this expression cannot be more than that voltage. If that voltage becomes too high, the V becomes too big, then all of this physics
okay.
Go it in the garbage and get another physics to do it, to help you with it. Okay? So what we're saying in here is, for question 2, is the speed cannot exceed that. So what is the acceleration voltage? This is the maximum voltage you can use for this lab. So while you're going on the knob in here, trying to adjust this voltage, here is a knob actually. I'm sorry, you guys are kind of living in an era where I have to show you things. I wish we are in the lab and show you where the voltage is that you're going to accelerate stuff in. You have to keep a watch on this voltage in here not to exceed that value. Okay, here's the voltage, I'm sorry. Okay? Otherwise, you're going to have a disaster before yourself. I mean, it's not going to work. The ratio that you're going to get is a big problem. So, assuming that this is done, this is V. I'm going to go again. V has a square root of E over M in it already. I know you have a 2 in delta V. Forget about the 2 in the delta V for a moment. But it has an E over M in it. And then you have an E over M up there that involves V. So E over M has a V in it. So if you plug in the square root of something times E over M, square everything, and there will be an E over M squared on one side and E over M on this side, cancel one of the squares, and you will be left with an E over M now in terms of everything else other than V. And everything else other than V is obviously the potential, delta V, and you have the magnetic field itself, and the R squared. Okay, so far so good. Now, here is the actual apparatus. What you have in here, you have 2 magnets. You would want the region between them to have a uniform magnetic field as much as possible. So you have an n number of coils on one side and an n number of coils on the other side. That is actually the experiment, how it's set up. And the beam comes in here, you would want this region to have a uniform magnetic field. Well, the magnetic field depends on how far you are. So you would want the combination of the two to give you as much as possible uniform magnetic field. If you do that, then you have a value for B naught that you're going to plug it into this expression. And if you can measure how wide, you measure how far is this one, this side of the beam, and how far is the other side of the beam. Subtract the 2 and divide it by 2. That is the radius r that you're going to plug it in here. This is how far basically they have deviated, okay, according to the cyclotron effect that I mentioned in the beginning. And you know what's your voltage. Hopefully you did not exceed that voltage from question 2. And now from here, now you're in business. You can find E over M. Does this sound like it's a good plan? Okay, so basically, if we are in the lab and if we are experimental physicists, and if we don't know much about the theory, we don't care about the theory, we don't care about what other people have done. That is the constraint. We know this formula works as long as we're in classical physics. My concern is find a B that is more or less uniform in a regional space. And if I can find how much a spread it is, then use this formula, and I know how accelerated they are. As long as I'm careful with my measurements for that voltage not to exceed that limit, then this formula should give me E over ME. And it should not be too different from the value that is known now today. This is taken as a known value. Where is it? This value, take it as a known value, because now it's taken as being basically a fact. So our experiment should give us an E over M that is of this order. Okay, so let's continue with this setup. Here is a problem though, B, trying to keep it fixed. If you guys remember, when we did the loop, a single loop only, okay, it has a mu naught times the current times the A squared. A in this case is just R, and we called it R, I think, in the lecture, okay? R squared divided by 2 times how far we are from it. And we call it X in the extra in that directed problem, but in here it's called the Z axis, that's all. So we called it the X axis in here. So when we did it in lecture, we found that it's mu naught times the current times this distance squared, which was, we called it the radius squared, divided by 2 times open parentheses X squared, how far we are from it. Since we are somewhere in the middle, and here it's going to be a Z component in here. So it's going to be Z squared plus A squared to the power 3/2. But I have n terms. I don't have only one loop. I have n of them. So that's why I have an n in the numerator, because each and every one of them will give me a magnetic field, okay? But I don't only have one. I have 2 of them actually separated by distance 2d. So this is a contribution. So any points in between them, any points on this axis, let's take this as the origin. Any points in here, if it is Z distance from this one, it's at a distance 2d minus Z from the other one. Since I'm using the same, the origin is in the middle, I'm sorry. The origin is somewhere in the middle. So if it's a Z distance in this direction, so it's at Z distance plus A from this one, and it's from this Z distance minus D, because this whole distance is 2d. So this distance in here is D, and this distance is in here is D. So if it is somewhere in here, it has a coordinate Z as a coordinate system in this representation. Then it's at a D minus Z, which is this distance from this one, and it's at a D plus Z from the other one. Which one is left, which one is right, it doesn't matter. The problem is 100% symmetrical, okay? So, but one of them has a plus D, and the other one has a minus D. The whole distance between the 2 coils is actually 2d, okay? The reason why I want this to be as smooth as possible. So I'm going to plot this function as a function of Z with a parameter D in it. In other words, how far can I make them so that the magnetic field will be more or less this shape, the red shape, okay? They are too close, it changes. The magnetic field changes a lot. If it is too far, it dips in and it changes also. So there is a nominal value in here that I need to find, and that is going to give you the magnetic field that is more or less constant. There is a video, actually I included for that too in the instructions that hopefully you guys will have a chance to go through, okay? So this is the function, basically B sub x. Remember that plotted function that I have in here? I can take mu naught Ni A squared completely out of the picture and here to the other side. and now plot this function as a function of x, because remember, I can only plot function y as a function of x. So this will be 1 over 2 times x plus, I'm going to also pull in here something. I'm going to pull an a out of the way, okay, because a is the same thing for everything in here, since it's a constant. So we'll have an a squared to the power 3/2, so it's going to be a cubed, cancel the a squared. So I'm going to have mu naught ni divided by 2a is going to be coming out of the in here on the other side. So I'm going to plot 1 over, this will be 1, plus z over a, I'm going to call it x, and d over a, I'm going to call it whatever, c, okay, constant c, because I'm going to parameterize it in terms of c, okay? And the same thing in here, everything else is going to be a 1 in here. It's going to be x minus c, the same c as in here, plus 1, and everything else to the power 3/2. So if I'm going to plot it, that's basically to give you an idea how you plot this one without having to lose a lot of generality. So in this case, it's going to be relative with respect to this one. So that's going to be my y-axis, and the x-axis will be just this variable in here. But I have a parameter, which is c, which is indirectly the ratio of d over a in this case, okay? So if I do that calculation carefully and plot it, this is how the graph would look like, depending, of course, on the parameter c. The plot could be flat or peaked or have these two peaks in it, okay? Actually, it could be more complicated than this. So what I'm going to do now, I'm going to go to the place where it's equilibrium and do this Taylor expansion around the z equal to 0. And if I do the Taylor expansion, I require that my b1 is equal to 0, okay? It's going to actually come out to 0 by taking the derivatives in here. This is the Taylor expansion, by the way, around b equal to 0. And if I do the around z equal to 0, if I do this one, this will be the first derivative. So you're supposed to do this. You're supposed to, first of all, plug in z equal to 0 in this expression. Z equal to 0 in this expression will give me a 0 here, will give me a 0 here. So this will be just twice as many of this term. So you will have a d squared plus a squared to the power 3/2, and the 2 is gone, and the numerator stays the same. Now that is supposed to be easy, okay? So the only thing that is gone is in here. So sub z equal to 0 in this expression. Then take the derivative of this function with respect to z. You need a big space, okay? You need at least 2 pages in here to make sure you're doing it meticulously. If you have access to a device that takes derivatives, do it. Let me see if I can do it with this calculator. Stop sharing the screen and share with you this calculator. No, I'm not sharing. Let me first of all make it bigger. Go back into my share. I forgot what the name of the derivative is called, I think. Is it called deriv? Forgot. Let me check. Is it deriv? No. Yeah, very good. So I'm going to try to do it in here, and you guys can basically, if you have access to something, you can do it in here. Because I have a bunch of parameters in the numerator, I'm going to just take them to the other side and make that as my function y, okay? So again, I just called basically what I'm doing in here. So the function I'm taking the derivative is 1 over, again, the 2 also was gone. So what I have in here is open parentheses, x plus c, the whole thing is squared, plus 1, because I took that as a common factor already, to the power 3/2, okay, plus 1 over, same thing in here, open parentheses, open another parentheses, I have x minus c, the whole thing to the power 2, plus 1 to the power 2, which is just 1, to the power, open parentheses, 3/2. The whole thing is no, I need the derivative, the variable I want to take the derivative with respect to. Okay, so this is a derivative. Now I need to put x equals to 0 in this function. So x equals to 0, that is z equal to 0 for you guys, okay? So I'll have minus 3c over this whole thing, which is the same denominator as this one, by the way, because when x equals to 0, we'll have minus c squared, and plus c squared is the same number. And in here, I will have, again, plus 3c, and x is equal to 0. So this should give me 0, because the denominator is the same, and the numerator is the same. Now I need the second derivative. This is when it gets a little bit uglier, because you're supposed to get all the way to, yeah, the second derivative. You're supposed to find the second derivative. I'm going to do the same thing as before. So I'm going to say derivative. This is a calculator I have, so hopefully you have access to something. If not, you can do it by hand, okay? And if you don't know this, so probably this is a trick that you can help you with your calc classes, so that you can take derivatives. So I'm taking the derivative of the derivative with respect to x, so that means I'm taking the second derivative. And this is how the derivative look like now, the second derivative, okay? So obviously all I did is just copy the derivative in there and told it to take the derivative with respect to x. And I'm calling c as being the ratio of b over a. And everything else in the numerator, I just throw it to the, as part of the multiplying everything by that, okay? So there is a big factor that I'm not writing into here. And that factor, if you want to really be careful with it, is mu naught. No, what is the mu? Is it like this? Mu naught ni divided by 2a. There is this factor that I'm not writing in this expression, that I have to multiply everything by it, okay? Because there is an a squared in the numerator and there is an a cubed in the denominator, so that will give me an a in the denominator, so I took that out completely out of the expressions. So if I need really the correct answer in here, I need to have this, and I also need to make sure that c is equal to, obviously this is not the value that it's supposed to calculate. C is equal to just simply d over a. Okay, so if I do that, I'm going to restore the same values basically with the trick that I just did. So now I put x equals to 0, so there will be a 0 in here, there will be a 0 in here, there will be a 0 in here too, and the denominator in here will have this c squared plus 1 to the power 5 halves. This is what c is. And the same thing in here, I will have c squared plus 1 to the power 7 halves. And in the numerator, I will have 3c times 5c, that's 15c. And then I have 3c times 5c, that's 15c. 15c and 15c, and the denominator is the same. So it's going to be, what, 30c, and you have so many things in here that don't involve c. Anyway, so you're supposed to, let me stop sharing the screen in here, and let me share with you the instructions. You're supposed to take the derivative with respect to, first of all, find b sub 0, which is easy, just plug in 0. And that should give you this answer. And b sub 1, you should be able to find it to be 0. I just showed you guys that it can be, the first derivative was actually 0 at 0, okay? So b sub 1 is the derivative of b with respect to z at the center, right between the two coils, between the two Helmholtz coils, okay, right in this place in here. So the first derivative is 0, regardless of which shape you're looking at it. It's either a maximum, or it's flat, or it's a minimum. So that's what that means, okay? The first derivative in the center is always 0. Now, the second derivative is the one that is this expression. The second derivative, which is the derivative of the derivative evaluated right in the middle. And I did that too using this calculator. I want you guys to, if you have access to a calculator that can do it for you, great. If you don't have access to a calculator, you can do it manually. This is not hard, okay? And then, given that b sub z is an even function, would you agree that b sub odd is equal to the odd derivatives, okay? So this b3 is actually going to be 0 also. So you don't really need to calculate it. All the odd derivatives are going to be 0. So consider the term b2. If d is less than a over 2, then b2 is negative, and then b sub z is concave. Down on the other side, if d is greater than a over 2, then B sub 2 is positive and the function is concave. What would it be if D is exactly A over 2? So you're going to sub the value in here for A over 2 in the other expression. In other words, C is just 1/2. So you're going to sub that value of C 1/2 in the function that I did and see what it would be. So that is how you have chosen it. Obviously, if you look at this expression, if 4D squared minus A squared will determine the sign of everything. If D is less than A over 2, obviously this thing is negative. If D is more than A over 2, obviously this is positive. If D is equal to A over 2, obviously it's 0. So that is the case that you would want to have in this case. Okay, second derivative also is 0. So to a higher degree of accuracy, B naught is some value, which you can find in here. B1 is 0 because it's the odd derivative. B2, you have selected it so that it's 0 now. So there is no Z squared contribution. There is no Z cubed contribution because that's an odd derivative. So the first correction coming from a higher order is Z to the power 4. If you make this choice. If you're careful enough with the lab and you do it this way, you are here. B hardly changes with Z as long as you move not too far from it, because that's what the Taylor expansion got you. Does this make sense to you guys? At least mathematically, forget about the physics in here. It's long and tedious, but it's doable. So basically, if D is equal to A over 2, everything cancels. The only thing that is going to be kept is B naught. This is 0 because the derivative of an even function in this case is going to be 0. This is a 0. This is 0 by choice. So the only thing that is going to be left is B sub Z is equal to B naught, which does not change, and that's what I want. I want so that when I'm doing my lab, I don't want the magnetic field to change that much. I want to plug in that value in here that I just found. Okay, because if it changes, then we have a problem. And it's just the geometry that dictates that. So when I plug in the value, so B naught now, for that value that we just said, for D squared is equal to A squared. So in this case, D squared is A squared over 4. So it's going to be A squared over 4 plus A squared. That's going to be A squared, 5A squared over 4. And you square it, and the 4, when you square it, it's going to be 8 when you bring it up in the denominator, and there will be a 5 in here, times the square root of 5 times everything else. So it's just subbing this value of D into this expression. This value of D into that expression. Okay, so now we're ready to do the lab, actually, after we go through all of that thing. Click on this one in here, and it's going to take you to the simulation in here. So let me stop sharing that screen, and you will see how easy it is when it comes to that part, and share with you this simulation. And now you're supposed to, if you read the instructions, and this is what you do in the lab, by the way, you change the values of the voltage between, you start with 125, then you move to 150, then you move to 175, and then you move to 200 volt, yanking the current from 1 amp, 1.25 amp in each time, 1.5 amp, 1.7 amp until 2 amp, and then you repeat. Each time you're supposed to take the readings for how far the beam is on one side and how far is it from the other side. You take the difference between them, or actually the sum because it's on one side, and you divide it by 2, and that is going to be your radius R. And you take the reading of the voltage that is given to you now for the delta V, for the accelerating voltage. So I'm going to, are you guys looking at the E over amp simulation, or are you going to go at looking at the PDF file? Because I forgot what I shared.
We can see the GeoGebra.
Simulation?
Yeah, the simulator.
Okay, so we're going to put in here 125 volts. And we are ready to collect. So usually you don't run it too long, okay? You just run it enough to get the data. And this is your data. So all I'm doing now is take this readings of the data and plug it into the Excel file that you guys have. So you have the 1M, you have the V, which is 120. So I'm going to stop sharing that screen because all of this data, you should see it on the table. So I'm going to put it on the table first, share the PDF file. So it's giving me delta V, the accelerating voltage, the first one, 124.33. I'm going to put 124.33 in here. This is for 1M. It's giving me L1 to be 5.73 centimeters, and it's giving me L2 of 14.48 centimeters. Same thing. I have L1 for this, L1 for the next voltage, which is 124.13. So this is 124.13. This is 6.79, and this is 14.43, and so on and so forth. So I plug in all of that data into my table, and then assuming I did all of this, I'm going to go in here and change the voltage actually to 150 volt now. And now the voltage is 150 volts. So now I have different values in here to plug in. So I go to the same table, but in the next basically group of cells. And then after that, let me see, can I change this one in here without having to reset 175? And now always try to reset this thing in here, okay? Always do new collection, okay? Because you might be have some data from before that is lingering, you don't want that, okay? So that's why it's a good idea to do off and then go back into the 200 volt and now collect the data again, okay? You don't want to rely on this. So if I'm going to do 150, I'm going to start it off first and then put 150 in here and enter. Once you enter, you get the collect button. Now you have a new data to work with. So now you know how to fill your table with the data. If we were doing it in the lab, this will take a long time to get all of your data, by the way. You'll be working in teams and it's really laborious work, but you guys should be able to do it, okay? So now you have your data. What you do with this data, you take it to the Excel file. So let me show you the Excel file. Where is the Excel file now? Yes, I did not open the Excel file. Let me open it first. Okay, there were some people who complained in the past about the solver not working for them because they had to enable the solver. So there are two Excel files in there. One of them, it says unprotected. You can use the unprotected solver, the equation, okay, Excel file. Don't rely on the one that is the other one because it's not going to work for you. You try to change the solver and follow the instructions, and it's not going to work for you. So, and enable editing. So when you come to it, let me stop sharing whatever I was sharing, if I was ever, and share with you the Excel file. This is the same lab in here that it is asking you to do this one in here. So you take the data that you have for the delta V in here, you take the different L's in here, and it's supposed to give you all of these things. And if you look at the lab instructions, at some point it's going to go to tell you to go to the, what is the instructions again? Transfer the data to the Excel file, and what is the, excuse me 1 second, let me find what a solver is. So we're going to go to options. Where is the Excel file? Are you guys still looking at the Excel file or not? Or did
Yeah,
it
we
move
are.
from? Okay, I moved this from one screen to the other screen because I have so many things on that screen. Okay, so we're supposed to go to options. What is the options in here on this version of Excel? Options. Come on. Okay. And we're supposed to go to add-ins. Okay. And we're supposed to find the solver in here under add-ins. Here is a solver. Okay. And that is on page 10 of the instruction all the way to the footnote. Okay. If it is not there, do the following: file, options, add-ins, solver, add-in, and then go. Okay. Here is go. And then at that point, you're supposed to say the solver add in, and now you have the solver up and running, okay? So you need the solver up and running, and then you're supposed to find, okay, hold on, let me stop sharing the screen. Did you guys see how you add the solver or not? Because it says, my screen says that it was paused or something.
Yeah, it looked like it was kind of frozen when you were trying to show that.
Okay, let me go again one more time, okay? Share the Excel file. So what we're going to do in here, we're going to go to File, Options. Under Options, we're going to go to Add-ins. Under Add-ins, we're supposed to find Excel. It's already added. That's why it's not an option anymore. Since I already added it, it's not listed in here as one of the add-ins, okay? So you're going to find it, and you hit Go, okay? Let me see if I can add another add-in in here. Let's do this one, for example. It's going to be one of these options in here. I'm going to say Go, for example, and now you see that I already added it in here. That's why it was checked. Then you're supposed to say, okay. You're supposed to go to the NOAA's website and enter the location that we're in. Namely, if you don't find it, just enter the address of the college, okay? Enter the address of the college, and should give you the coordinates of the college, and enter also the elevation of the college, which is 640 feet. And once you're there, note that 1 Gauss is this many 100,000 nanoteslas, okay? So we're going to give you the value of the magnetic field of the Earth in that location where we're supposed to be doing the lab. So you're going to go back into the Excel file and plug it in there, okay? And then you're going to follow the rest of the exertion. Now you will see solver add-in. So now you're going to have that and go to the data and data tab. And under data tab, you're going to solve. It's going to improve basically your reading for E over M, okay? So you're going to click on that minimum, and then you're going to have the instructions. Once you solve it, you're going to have a ratio for E over M. Once you do that, you have everything you need for this lab to draw a conclusion on the ratio of E over M. Sounds a lot, doesn't it? And it is, even in a simulated environment. Yes? Okay, so what I'm going to do now, I'm going to stop. So first of all, stop the recording, and then turn off my, mute my microphone and stop my camera. If you guys choose to stay and work on it now, that's great. If not, then you have until the deadline to submit your lab. You can work in Teams again too if you want to. Sounds like it's a good plan?
Sounds good.
Okay, so I'm gonna stop the recording first.